Welcome back to our free Euclidean geometry tutorial. Right, so this is part 6 out of a total of 10, and we'll be looking at tangents, which is the last part. Okay, the first theorem that we'll be looking at under tangents is the one that states that the tangent to a circle, right? First of all, we need to define what a tangent is, right? By definition, a tangent is a line that meets the circle at one point and one point only. What I mean by this is that if you have a circle that looks something like this, say you have this circle right here, this line can be a tangent if the line meets the circle at one point there, which can be point P or something like that. But this will not be a tangent. Why? Because it intersects the circle at 2 points now, which is that and also that. Okay, so the first theorem under tangents, which states that the tangent will always meet the radius or the diameter at a 90 degrees. The tangent to a circle is perpendicular to the radius or diameter. Remember, a diameter is twice the radius. A diameter passes through the center of the circle, right? Yeah, so it's perpendicular to the radius or diameter of the circle at the point of contact. As you can see now, point B is where that line AC meets the circle. So since OB is a radius, then by default this should be a 90 degrees. A radius is always perpendicular to a tangent. So that's the reason. Tangent perpendicular to radius or tangent perpendicular to diameter. Remember, this would be a diameter if we extend OP all the way to the circumference, like that. Okay, and you do not need to know the proof of this. This is more like a fact that you should know. Okay, and let us see how we use this. Look at that. Given that APT is a tangent, so in all these problems, APT is a tangent and also O is the center. Right, and O is the center of the circle. So what we have is find angle X. Before we can find X, what do we need to do? We first need to find that angle there. Let's first conclude OP, the line OP will be perpendicular to the line AT, right? Because OP is a radius, AT is a tangent. Why? Because a tangent is perpendicular to a radius, like that. Okay, which means then OPT, the angle OPT will be equals to 90 degrees. Why? Because we just proved that OP is perpendicular to AT. So once we have a 90 degrees there, then you can see that X will be none other than 90 degrees minus what? Minus 50 degrees on angles in a triangle, right? Just like that. So X, which is none other than 40 degrees in the first example. So the second one, find X, Y, and Z. Which one can we find first? First things first, let's find X. So we can see that the line OP has to be perpendicular to the line AT because OP is a radius and AT is a tangent, right? How do we know that it's a radius? We said O is the center of the circle and the line OP runs from the center to the circumference, making it a radius. So OP is perpendicular to AT because a tangent is perpendicular to a radius or diameter. In fact, the line BC is a diameter. Whatever you wanted to use, OP or CP, either one of them is fine. Which makes the angle OPA will have to be, hey, don't forget that this is an angle. OPA has to be equals to, and this is angle X, OPA is equals to 90 degrees because the line OP is perpendicular to that tangent AT, right? And then from here we can see that X will be none other than what? Than 90 minus the 35, because this whole angle right here is 90 degrees, right? You don't need a reason for this, which makes that a 55 degrees, like that. X is 55. But once we have X, we can find Y. Remember, the line BC is a diameter, making angle Y equals to what? Equals to 90 degrees. Remember, this is a special case. A diameter subtends a 90 degrees at the circumference, right? So these are angles on a diameter or angles in a semicircle, right? And then moving on, we can find Z. Z by default has to be equals to 90 degrees minus 55 degrees, Why? These are angles in a triangle. And then by default, angle Z will be equals to 35 degrees. Okay, let's move on. Here's my favorite theorem, which is the Tan-Chord Theorem. So this one states that the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment. And the reason for this is Tan-Chord Theorem. So in simple terms, we're going to try to relate this to, remember the exterior angle of a cyclic quadrilateral. Right, so first things first, when you want to apply this theorem, you need to make sure that you have a tangent. Right, and on top of that, you need to look for a triangle inside the circle such that that triangle touches the circle circumference at 3 times. Those are the key things that you need to look out for. Also, we spoke about the Z shape when we were doing the exterior angle of a cyclic quadrilateral. So even for this, what this one actually says is that this theorem tells us that the angle between a tangent and a chord, right, between a tangent and a chord is equal to the interior opposite angle. If you say interior, you are referring to this interior opposite, which is that. So how I do it, I do that Z-shaped thing. Then I'd be like, if these were parallel lines, this would have to be equal to that. But it said interior opposite, so we skip this, we take that. Okay, in simple terms, let's check. The angle between a tangent and a chord, this angle between a tangent and a chord is equal to the interior opposite angle, or the angle in the alternate segment. It's that and that. Also, this one, instead of taking this and that, you skip this, you equate it to that. Makes sense? So it's what we have exactly here. Look at it. AC is a tangent. So the angle between that tangent and this chord is equal to the interior opposite angle. Same thing again, even on the other side. This angle right here has to be that interior opposite angle. And that triangle which you are referring to must touch the circumference of the circle 3 times. Okay? So let us go ahead and prove this theorem. Right, so for all the theorems that we've proved up to so far, there's different proofs. It's up to you which one you prefer. Okay, let's take this one whereby we have this tangent right here. Let's say we are given this triangle which touches the circle circumference 3 times, and we are given center O. Let's call this one A. A, B, C, and this is D and E. Right, this is B1 and that's B2 at this point. In fact, let's not name it B1 and B2. So you state first, what are you required to prove? Start here. You first need to state what exactly are you required to prove. Right, you are required to prove the following: that the angle CBD, which is this angle right here, has to be equals to the angle E. Is equals to angle E. The angle between a tangent and a chord is equals to the interior opposite angle, or the angle in the alternate segment. Right, and then what are you given? Okay, at least here I'm given a circle with center O, which is written like that, and then I'm also given a tangent. Tangent what? Tangent ABC. Right, so next step, remember you should construct when you prove a theorem. So this theorem can be proved in 2 ways. There's some people who use that construction there. Right, you go and learn this, but for me I construct this radii. So I'm just going to construct the line or join OD and OA like that. OD and OB, sorry. OD and OB. Right. Okay, such that now this becomes angle O1, that's angle O2. This becomes angle B1, that becomes angle B2. That becomes angle D1, that's D2. It's up to you how you name it. Okay, let me just call it D2, D1. Let me put the 2 inside, like that. And then the proof itself now. So you let angle E equals to X. When you let this one equals to X, then by default you can see we have that arrow thing, the one we spoke about on angle at center. the angle O1 would then be twice what? Would be twice of x. Twice angle x. It's twice angle E. Why? This is angle at center, which is what? Which is 2 times angle at circumference. Okay. So now we have this one. Since this is x, that's 2x. But then if you look at this, you will see that the line OD is equals to OP, and this is none other than a radii. Okay, which then means that the angle B2 is equals to the angle D2, because these are angles opposite equal sides. Angles opposite equal sides. And then from here, we can work with what we have. In fact, if you look at the triangle BOD, in triangle BOD, we have the following. If we add the angle B2 to the angle D2 plus the angle O1, this should give us 180 degrees. And these are angles in a triangle, sum of angles in a triangle. But we have these two to be equals to each other. So we can just say it's 2B2 plus O1, which was calculated to be 2x, is equals to 180 degrees. Transpose that, we have 2B2, 2 angle B2, which is 180 degrees minus 2x. Then divide everything by 2, right? Which gives us what? That the angle B2 should be equals to 180 divided by 2 is 90 degrees. 2x divided by 2 is x. So we have this angle to be 90 minus x. We have that to be 90 minus x as well. But remember what we said. OB will be perpendicular to AC. Why is that? Because a tangent is perpendicular to a radius. Right. And then from there, this means that the angle OPC, the whole of OPC, this angle right here, should be equals to 90 degrees. Why? Because OP is perpendicular to AC. Then from here, this simply means that the angle B1 plus the angle B2 should give us 90 degrees. But we do have B2 to be 90 minus x from the previous step. So we carry this here, which gives us the angle B1 now. B1, which is 90 minus B2. But this is 90 minus, remember B2 is 90 minus x, which gives us a 90. Expand that, minus 90. This times that, which is plus x. So this cancels that. And then we end up with angle B1 being equals to x as well. But remember, angle B1 is none other than the angle CBD, the one that we are looking for. So that's the proof. Okay. Now let us apply this real quick. There you have it. This is how they prove it. And I told you, the theorem numbers don't really matter. You just have to know how to state the theorem. This one tells us that the angle between the tangent to a circle and the chord drawn from the point of contact is equals to the angle subtended by the chord in the alternate segment, or is equals to the interior opposite angle in simple terms. Right. So yeah, you will learn how to prove that. Even for this, it holds. Let's check it out. Look at this triangle right here. It touches the circle circumference 3 times, so that's the one. But then look at the tangent. Here's our tangent. The angle between a tangent and a chord equals to the interior opposite angle, which is that one. Makes sense, right? So here we go. Okay, then here's something which you shouldn't do, that I've seen people do, especially with this theorem. It becomes a bit tricky, right? When you have this now, let's say you have a chord like this, and then you have the circle center there, then you have this and you have that, right? So this angle right here is not equals to that angle there. They are not equal to each other, even though like it looks like it's the Tan-Chord theorem. Why is it not? Because O is the center. That's the center part of the circle. You cannot equate anything to the center. In fact, up to so far, we only spoke about one theorem that allows you to equate things at the center, which is what? Which is none other than the theorem that states that equal chords subtend equal angles at the center of the circle. That's the only theorem that allows you to say this is equals to that. Right? Otherwise, the center is always twice something. In fact, this theorem would only apply if you had what? And we did speak about, just look at the triangle. One, it's not at the circumference. That triangle only has 2 points at the circumference. Hence, the Tan-Chord won't apply. but the one which I just drew has all 3 points at the circumference, which means this angle right here would be equals to that angle there, and also this one right here would be equals to the whole of that right there. So you need to be careful of such. Okay, and yeah, we move. Let's look at this again. Here we are given that APT is a tangent. I just cut out the statement. So in all these problems, APT is a tangent. Let's look at that. We need to find xy and what? Okay, xy in the first problem. Let's see, how do we find x and y? We check APT is a tangent. Let's look at we see this 1, 2, 3 times. It touches the circumference of the circle 3 times. So we can apply the Tan-Chord theorem. Remember, the Tan-Chord theorem says what? This angle right here, you skip that, should be equals to that. So x has to be equals to 30 degrees. Why? Because of the Tan-Chord theorem. Okay, there you have it. We need to find angle y. How can we find angle y? Now this is where everything comes into everything combines. We spoke about cyclic quadrilaterals. If you look at this, that quadrilateral touches the circumference of the circle 4 times. So we have a cyclic quad there, which means we need to find angle q first so that we can use sum of angles in a triangle. Right, and it's tempting. It looks like the line RP is a diameter. It's not, because they did not tell us. So you making that assumption that this is a 90 degrees, that's a deadly thing to do. What looks like might not be. You just have to prove it first. Okay, so let's go ahead. First, we are going to find angle q by saying angle q is equals to 180 degrees minus angle s, which is 100 degrees, and these are opposite angles of a what? Of a cyclic quad. Like that. Okay, so we have angle q, which is equals to 80 degrees. Once we have that, then we can do y. Remember, y plus 80 plus angle y plus 80 degrees plus 30 degrees should give us what? Should give us 180 degrees. Angles in a triangle. Right, then we have that y plus this, which is 110 degrees, and this should give us what? It should be equals to 180 degrees. So y, which is equals to 70 degrees in the end. Makes sense? Let's look at this. First of all, we are given that these two sides are equal to each other. PC is equals to CD, which means this is also x. So angle D will be equals to x. Why is that? Those are angles opposite equal sides. It's an isosceles triangle. Right. Then from here, Tan-Chord theorem applies. Remember, this is not equals to that, but is equals to that. So angle x is equals to what? Angle x will be equals to 80 degrees. Why? Because of a Tan-Chord theorem. Makes sense. Okay, let's move along. Let's look at this one. You're supposed to find x. Again, Tan-Chord theorem. Look at this. You have that this touches the circumference how many times? 3 times. So then the Tan-Chord theorem can apply in this case. Can apply that to give us what? To give us that this angle right here is equals to that. So angle x is equals to 35 degrees, Tan-Chord. Right. And y as well. Look at y. If you look at the triangle, you have that this, that, that. So you have this triangle right here. So there's 2 ways to find y. Either you go for the Tan-Chord theorem, whereby this is equals to that, or you go for angles in the same segment, y being equals to x. They are both subtended by the chord BD. So y is equals to x, and they are both equals to 35 degrees. Reason, angles in the same seg. If not angles in the same segment, then it has to be Tan-Chord theorem. Okay. Yeah. Let's look at a bit of combined problems. We cannot do problem number 1 as yet. We'll do it in the next part. Let's do number 2. Given that statement, O is the center of the circle in each case. In each case, determine the value of A, B, C, and all that, clearly stating your reasons. Again, we are going to be doing this alphabetical order like in the previous exercises. So for now, let's look at number 2. Okay, let me just do this. Let's just crop this out. We know the statement. We only need the fact that this is a center and that is a tangent. Okay, so let's go for number 2. Okay, so on number 2, there you have it. Where is angle A? Angle A is that one. It's an angle at the center. It's a central angle, as you can see, which was subtended by the arc what, or the chord RQ. So this goes on to subtend angle A at the center, but subtends another angle of 52 at the circumference. So by default, angle A has to be 104 degrees, and that's what? That's angle at center, which is equals to 2 times angle at circumference. 2 times angle at circumference. Okay, and then we need to find angle B. Where's B? B is the angle between a tangent and a chord. But which triangle can we use? This one, because it touches the circumference 3 times. So in fact, angle B should be equals to what? Should be equals to 52 degrees. Angle B is equals to angle P is equals to 52 degrees. And this is the Tan-Chord Theorem. Right. So that's what we have. We have B. Where's angle C? Look at angle C. It's right there. But at angle C, you can see that the line OR is perpendicular to SR. Right? OR will be perpendicular to SR because of what? A tangent is perpendicular to a radius. And then from here we have what? We have that angle C will be equals to 90 degrees. Why? Because OR is perpendicular to SR as proved. As proven in the previous one. Right? And then what's D? D is that angle there. How will we find D? It's a bit of a tricky situation, but it's doable either way. So let's isolate that triangle, the one which we have to use. If you look at this green triangle right here, you will see that actually the line OQ will be equals to the line OR, and this is a radii. And then if that's the case, if this is to be equals to that, it means the whole of that, the 2e is there. So 2e, 2 angle E, because it's E and E, has to be equals to angle D. And those are angles opposite equal sides. Right. Okay. And then from here we have angle A, which means we can now do what? Sum of angles in a triangle. Angle A plus angle D. Instead of using what? Remember we had 2e here. Should be 180 degrees, and these are angles in a triangle. So instead of using 2e, we are going to use D. Remember 2e is equals to angle D. So this will be A which is 104 degrees plus this is going to be 2D. Remember these are equal to each other, which is equals to 180 degrees, which means D will be equals to 180 degrees minus 104 degrees all divided by 2. Once you have D, then you have what? You have E as well. Now you need to find angle F and angle G. How will you find angle F? Let's think about it. What's the best way to go on about finding angle F? There's F there. Okay. We now have D. Yeah, you can find F. Look at the triangle. We just found angle E, right? Because after finding D, you just divide D by 2 to find E, because 2E is equals to D. Then divide like that, which means now you will have this angle right here, and you have this. But if you focus on that triangle, sum of angles in that triangle will give you angle F, right? And then finally look for G. How will you look for G? If you have this angle, then you would find G. If you have this angle right here, because G is vertically opposite to that angle, which is OVR. So if you can find OVR by using sum of angles in this triangle, then by default you have that, because they are vertically opposite to each other. Okay, let's move on. Let's look at the next one. Find x, w, x, y, and z. Let's start with w. We can see that w is equals to what? Since tu is a tangent, w is equals to 70 degrees on Tan-Chord Theorem. Right. How do I write this way? It's THM in short for theorem. Okay. And after having W, we can find X. How do we find X? Tan-Chord theorem again. You're coming from this side, you have that, you skip this, you take that. So X is equals to that. So X is equals to 50 degrees. What? This again is Tan-Chord theorem. Okay. So we have those two, 70. There we have a 50. Here we have a 70. So now to find y, it's up to you which one you want to use. You can use this straight line whereby you have y plus 50 plus 70, which is equals to 180 degrees, and these are angles in a straight line. If you do not want to use that, then you could have used the sum of angles in this triangle whereby you have x and 70 degrees. The answer would still be the same. So y is equals to 180 minus this plus that, which is 120. So y should be equals to 60 degrees. But once you have y, by default you have z, because this is a cyclic quadrilateral, and y and z are opposite angles of a cyclic chord. So z will be equals to 180 degrees minus that 60 degrees. And these are opposite angles of a cyclic. Okay. So that's how it goes, whereby z will be equals to 120 degrees. And that's that. See you in the next one.